Well, if A is a symmetric matrix, so that means equal to its transpose, there's a special property that the eigenvalues have to be real. So, I mean, that means they don't come in complex conjugate pairs. They're just real eigenvalues. And also, there's another neat thing, that if you get the eigenvectors corresponding to different eigenvalues, lambda 1 and lambda 2 not equal, then the eigenvectors are perpendicular to each other, which is really neat and useful and comes into lots of applications. So x1 dot x2 is the same as x1 transpose x2, and that's equal to 0. So the eigenvectors for different eigenvalues are orthogonal. Also, of course, A and A transpose have the same eigenvalues because the determinant's the same if you take the transpose. So, I mean, the eigenvectors will be different generally between A and A transpose for non-symmetric matrix, but A and A transpose have the same eigenvalues. Also, rather neatly, if the matrix is invertible, then the eigenvalue is exactly 1 over the eigenvalues of the original matrix. And of course, it also kind of tells you that the way it's not invertible is if any of the eigenvalues are 0. So when you have a factor of lambda in the characteristic polynomial, then you've got a singular matrix. In other words, if lambda equals 0 was an eigenvalue, well, I mean, clearly there's an x so that ax equals 0 and it's singular. Anyway, if it's non-singular, it's got an inverse, the eigenvalue is just 1 over. And actually, if you shift the matrix by a multiple of the identity, just shift the diagonals, of course it's the same as just shifting the eigenvalues if you think about the way they're defined. So this is sometimes important for calculating eigenvalues numerically, that sometimes you might want to shift it, say, to make all the eigenvalues positive. So that's quite a useful property as well. As well as the inverse, other powers of the matrix, and by power of the matrix I mean multiply the matrix by itself. So a squared is a times a cubed is a times a, using matrix multiplication. Of course they're square, so it always works, right? So integer powers of a and negative powers are just powers of the inverse. It turns out the eigenvalues, you just raise them to powers as well. So if you do a twice, it's the same eigenvectors, but the eigenvalues are squared. Now the trace is a handy thing that's sometimes important for matrices. The trace is the sum of the diagonals, and it comes up quite a lot in different contexts in engineering. And it turns out the sum of the diagonals is the same as the sum of the eigenvalues, which is a kind of interesting thing. This somehow there's kind of two really important sort of invariants of a matrix. One is the determinant, and the other is the trace. And the trace is the sum of the eigenvalues. And the determinant is the product of the eigenvalues. You multiply them together. That pi is a bit like sigma means sum, add them up from 1 to n. Pi, capital Pi for product, means multiply them together. So the determinant is the product of the eigenvalues. Again, you see if you've got any eigenvalue that's 0, the det's 0 and it's singular. Eigenvalues, eigenvectors corresponding to different eigenvalues have to be independent. So in other words, they're not multiples of each other. They're pointing in different directions. Maybe that's kind of obvious at least, but obviously you could have a multiple eigenvalue, that's a repeated root of the polynomial equation. That's kind of different. But if the eigenvalues are different, then the eigenvectors are independent of each other, which means if two vectors are independent, it just means they're not multiples of each other. They're not pointing in the same direction. But sometimes there are less eigenvalues than you think. And this little example is really a kind of archetypal example. And it's something that's very interesting. I mean, it happens quite a lot in things like control theory and study of oscillators and so on. So it's a useful example. Here's a matrix. Its eigenvalues is just 2 and 2, but it's got this off-diagonal term as well. So the eigenvalues are lambda 1 equals lambda 2 equals 2. In other words, they're repeated. It's a repeated eigenvalue. And then after the eigenvector, we solve A minus 2i, and we get this rather silly little matrix with lots of zeros. And you see, obviously, if I multiply that by 1, 0, I get 0. So I've got an eigenvector. You just solve this equation, you get that 1, 0 is an eigenvector. But even though it's a double eigenvalue, it's a kind of repeated root, we only get one eigenvector. Actually, if you've ever studied oscillators and you know what a critically damped oscillator is, that's kind of a case where you get a repeated root of a polynomial. Then this is exactly analogous to that. Anyway, this case we only get one eigenvalue, and you can kind of see why. So the eigenvector is t, 0, any multiple of 1, 0. Contrast this example, a really simple example. This is really just twice the identity matrix. It's got 2 on the diagonals. The eigenvalues are 2 and 2, but in this case, of course, any vector is an eigenvector. So for example, 1, 0 and 0, 1 are both eigenvectors. But actually, you can see in this case, any vector is an eigenvector. So we just choose 2 independent eigenvectors, and we've got two independent vectors in the plane at all, and they'll do as eigenvectors for the eigenvalue 2. So we've got 2 independent, at least, 2 eigenvectors, and we can write them as any ST, or if you like, multiples of 1, 0 and 0, 1. So without the 1 here, it was very different, and that's kind of an archetypal situation. So yeah, so which is eigenvectors we can take as 1, 0 and 0, 1. Okay, next we're going to do a 3 by 3 example.